sunny day. It's hard to get people inside the room. So
Wow.
it's good to have a good audience. And
Great.
I have the sheet with the assistants. So all the things you have to do for the course, I have it there. So remember to do that. And why don't we do a brief introduction before we start?
Sure.
Seth Price, undergraduate, civil engineering department.
I'm a transportation engineer. My first good traffic engineer was a graduate of Texas A&M.
Was it? Okay,
Dr.
good.
Zachry Humphreys.
Good to know.
Before your time.
Probably. Oh, okay.
Robert Esposito, CE undergrad.
Ryan Conrad, graduate student at CE.
And we have master student in civil.
Alex Pagazzi, civil engineering undergrad.
Bob Keller, graduate student in the Master of Urban Regional Planning program.
Always Zahir, undergraduate civil engineering.
Alan Delatorre, urban studies. I work at the Institute on Aging.
Waitho, civil engineering graduate student.
Nikki Wheeler, civil engineering graduate student.
I'm David Relos. I'm a master in urban and regional planning, and I'm also a Trojan.
Oh, you are? Okay, good.
I'm Heather Spalding. I'm a graduate student in the science department.
I'm a graduate student in
Sure, Ryan Gratzer, staff at the Center for Transportation Studies.
There's the public very interested in meeting you. I hope to come to the next two also, but the ones after that wouldn't relate to me.
I'm the undergraduate in legal studies.
Getting into the plan.
Okay.
I don't know that.
Each several courses, trade, transportation modeling. We'll talk more.
Okay, so it's my turn right now. All right, so good morning, good afternoon, everybody. I don't know if you're in the middle. My name is Luca Quadrifoglio. I'm from Italy and currently an assistant professor in the Department of Civil Engineering at Texas A&M College Station. And today I'm going to talk about the zoning strategy effect in the ADA paratransit services, and specifically a simulation study that I did when I was in Los Angeles. I was hoping to bring here a new study that I'm still doing right now in Texas, but I didn't manage to get results done, so I said it would be much better if I speak about this one, which is complete. So since you made an introduction about yourself, I thought that the first slide was just, who am I? And first of all, I'm not a civil engineer, okay, even though I'm teaching a civil engineering department. Actually, I started with chemical engineering in Italy, and then after that I worked for 5 years in the Eni Group. It's a major Italian oil company. And then I decided to quit my job and to come to the US, and here I am at USC, Master in Engineering Management, and then all my doctoral study, same department, in Industrial and System Engineering. So I consider myself an OR guy, Operations Research guy, and I did all my dissertation on applying operational research technique on transit and transportation system in general. Here they are. My research interests are related to the broad field of operations research and its variety of domains, and they are focused on improving system efficiency and performance and helping in the decision-making process in general. Particular emphasis on transportation system, specifically transit, and the talk I'm going to discuss today is an example of that. So introduction about what are ADA paratransit. How many of you know what a paratransit system service is, or what they do every day? Most of you. It's a big business. In a city like Los Angeles, they have 8,000 to 12,000 trips requests every day, and they have to manage to pick up and drop off these customers, which are disabled, most of them. And in 1990, the American with Disability Act was a big change in the business because There were higher mandated performance standard, and as a consequence, these services are highly subsidized with a very high operating cost. Therefore, most of transit agencies are eager to identify cost reduction and productivity improvement because it's a high cost of having these mandatory services going on every single day. How do they operate? Well, there are several variations across the US, but in general, we can summarize the operating practices with these few points. Few customers are served in real time. Most of the customer is booked in advance, generally 1 day before. And the demand is scheduled, once it's collected, is scheduled the night before the day of operation, where the customers are assigned to vehicles and the vehicles are assigned to drivers. It's a highly complex problem to solve, and I come from industrial and system engineering, and I know this probably a little better than the typical civil engineering just because it's not a typical topic of civil engineering, but it's one of the most difficult problems to solve in optimization, so it can be solved only with heuristic, which are approximation techniques. But believe it or not, still today, these scheduling problems are finalized manually, at least partially, after software initial solution. And the solution are generally far from being optimal simply because there is not enough time to solve this problem optimally. There are two major operating practices that affect the customer, which are the time windows and the maximum trip time. What are those? The time window is simply if you call for a service and say, I want to be picked up at 9 o'clock, the agency say, okay, we are going to be there between 9 o'clock and 9 o'clock plus a time window which is varying between 20 or 40 minutes, depending on the city or the part of the city sometimes. Specifically in Los Angeles, they use 20, and in Houston, they use 40. Okay? And then there is the other one, is the maximum trip time, which is K times the direct trip times. And also this parameter here, K, can vary from 1.5 to 2.5. And what is that? What does it mean? So that if I take a cab ride from where I start, from my pickup to my drop-off, it would take, 30 minutes. And the maximum trip time that these services have to guarantee to the customer is between 1.5 and 2.5 times the direct trip time. Otherwise, they need to pay a penalty or give some money back to the customer. So these are the main operating practices. There is another one that is the one that I want to focus mostly today, which is called zoning. What is zoning? Also identifiable as a decentralized strategy, and is practiced especially within large metropolitan areas like, of course, Los Angeles, where I did my study. And what does it mean? It means that the service area, the whole service area, as you know, Los Angeles is a very big service area, is divided in zones and served and managed by independent providers. So the pickup demand point decide the area of belonging of a particular customer, but the customer might be dropped off outside of the area, but just not picked up. Problems. The same customer might need two providers for its two-way trip because pickup are in different zones. And the overall operating cost might be higher, and we'll see that later. More miles driven by the whole fleet and more vehicle used, especially more the so-called deadhead miles, which are defined as the empty trip mile driven by the vehicle between drop-off point of a customer to the pick-up point of another customer. And the agency want to avoid that because it's basically a part of the trip which is not serving any customer, it's just a cost because you need to drive from point A to point B. So this is in a few words what we mean about zoning. And there is another zoning strategy, so-called with transfer point. I'm just going to mention to you. The service area is still divided in zones, served by independent providers. And again, the pickup demand point decides the belonging area. The customer going outside of the area cannot use the provider or their pickup area, but need to switch provider at transfer points. and this can cause major problem for people with wheelchair, because the transfer, the unload from one vehicle to the load to the other vehicle takes a lot of time and, of course, a lot of discomfort for the customer itself. Remember that we are talking about disabled people. And they also need the synchronization between agency at transfer point. So it's not very widely used across the US. So back to the actual study. Here is the Los Angeles County and the zoning, which is applied to Los Angeles County. We have a northern region, eastern, west central, southern, and then we have these two. This one doesn't work anymore. Anyway, the two on the north part are very small in density. Actually, we exclude them from the study because they are really significantly smaller in demand. So our simulation study was to evaluate the effect of the decentralized zoning strategy, which is what is actually happening right now, versus an hypothetical centralized no zoning strategy where you consider the whole area as a single zone and not divided. So we performed the study by simulation. We had actual demand available from the service provider, one of the service providers in Los Angeles, and we used the same scheduling algorithm in all our considered simulation options. And we want to see the effect of the different options on this performance measure here, or output, which are the total miles driven by the whole fleet, the total deadhead miles that I mentioned before, total vehicle use, the passenger miles, how many miles in total are driven by the passenger, and the idle time. There are some times where the vehicle needs to wait for a customer to show up with customer on board, and this is called idle time. I should have mentioned at the beginning, if you have questions while I'm doing this, please stop me anytime. I should have said that at the beginning. Sorry about that. So this is the demand, the actual demand we have. We have the 4 regions, as I said, and we are excluding from consideration the 2 at the north because they're very, very small. So this is a 1 day daily average number of trips without including the no-shows, which, as you can see here, is about 10% of the time. People and customers booking for a trip and not being there. It's another major problem that agency needs to face. So these are the daily, more or less, the daily demand of each one of the zones. And as you can see, 1/4 of them, more or less, 25% of them, are customers that have a wheelchair.
I think you also
Sure.
asked a question.
Sure.
I'm familiar with Indianapolis, and the city of Indianapolis could not meet the demand. Does Los Angeles, these are demand that were actually met?
This is the average of a week of operation. This is the average of a week operation without considering the no-show. So these are actually trips performed on average in 1 day, consider the average of the week.
All right, then let me have a follow-up.
Sure.
Would you know that if City of Los Angeles could meet all the demand?
Oh, you mean actually, yes, these are all served trips.
Thank you.
Yeah, there is a difference between no-show and not meeting the demand, but Los Angeles, as far as I know, right now is able to meet the demand because there's enough fleet to serve the demand. A little bit more detail on the demand. These are just 2 ways to say. A is ambulatory customer, which are still disabled, but they can walk. Some of them may be blind or may have any other kind of disability. And WC instead means, as I said before, people that need wheelchair. So each request, most of the time, actually not most of the time, sometimes, it's not only one customer, because these people need people that take care of them. So you have, sometimes it's only by themselves. Sometimes there is one person in addition to the actual customer, sometimes even 2, and in very few cases even 3. So when you have a demand, it's not only one person, it can be more than one, and this is going to impact the capacity of the vehicle itself. Just some statistic about the calling time when the people call for service. This is not very useful for our study, just to show you. Generally, they call in the morning or the day before. These are all the calling time the day before the operation, because, as I said, most of the demand is requested the day before they need it. And it goes from the morning to the evening of the day before. And this is instead is the requested pickup time, so when they need to be picked up at their location. And as you can see, there is somewhat the typical double peak, where you have peak hour at the morning and the second part of the afternoon, a little bit less during lunchtime, nothing during the night or almost nothing during the night, and going down during the evening there. And well, this is just to show that for our simulation, this is the cumulative distributive function of the chart that we just saw. The actual is the blue line, which is clearly not linear. In order to make our simulation work, we did some assumption, and we used the red line, which is a piecewise linear function, much easier to manage. It's not exactly as it is, but it's close enough, as you can see from the chart here. This is the location distribution. The greener, the more demand in a particular square mile. Each of the square is actually a mile, square mile. And this is the northern region of Los Angeles. And, well, you can see yourself, it should be pretty explanatory. The darker the green, the more customer you have in a particular square mile. And this is actually the drop-off. So people belonging to the zone, the northern region, not all of them wants to go in somewhere in the northern region. Actually, 20% of them needs to go outside, and this is the distribution across all the Los Angeles area. I don't know if you're familiar, here is Santa Monica area, and here is Orange County, here is San Bernardino area. Travel distance, this is distribution of how long is the travel for each customer. As you can see, the average is more or less between 9 and 12 miles. This is actual travel distance. And well, I don't want to go too much in detail with this, just to show you that in our simulation we try to independently sample the pickup and drop-off location of the customers. And if we do that, the resulting travel distance distribution, which is the green one, is not exactly matching what actually happened. But don't forget about the option 2 that I should have removed. Just focus on the green and the black. The black is the actual travel distance from the data, and the green is what we actually assumed, independently sampling pickup and drop-off. The disparity between the two is not too much, so we decided to go with an easier option, which is sampling independently. Again, I don't want to go too much in detail with that. These are the resources, how many vehicles the Los Angeles Transit Agency has to meet its demand. In the northern region, west, eastern, and southern, we have vehicle type 3A means 3 seats for ambulatory people, plus 2 customers that need a wheelchair, and so forth. The biggest one are this van here, which are in like a bus, 11 ambulatory people, and 6 wheelchair. But they don't have many of those, as you can see. The majority is this kind of little van, which is more or less big as a super shuttle van, the one that you see at the airport. Okay, again, for our simulation, the parameters, we made very reasonable assumption, actually taken from the data, most of them, so we didn't invent anything. The average speed of the vehicle is more or less 25 miles per hour. The distances are calculated rectilinear. Maybe some of you are familiar. It's not a Euclidean distance, but you assume that from one point to the other you go in a rectilinear fashion, like only following horizontal and vertical line. And actually, in addition to the scope of this study, we also double-check that this assumption is actually pretty good, that the Manhattan-like rectilinear distance actually does match pretty good the actual distance between 2 points, because you never go straight from one point to the other. Even though you have a freeway, you always have curves, and you have other deviation to do. So anyway, close the parenthesis about that. Service time also taken from the actual data. If there are no wheelchair customer, it takes about 30 seconds to pick up or drop off somebody. Instead, maybe you didn't guess that before that. If there is at least one customer with a wheelchair, it takes a lot of time just to load it in the vehicle itself and vice versa. This is not a mistake. It's not 10 seconds. It is 10 minutes. It's a lot of time to do that. At least this is what we got from the transit agency itself. And actually, I should say, this include a lot of other things, like when you get there, you need to wait that you get out of the house. It's not always ready there for you to be picked up. It takes quite a bit of time, on average. We use the 2.5 K factor, which is the one used actually by Los Angeles, and the time window, as I said before, is 20 minutes. Scheduling algorithm. We didn't do the study to improve the scheduling algorithm, so we used something reasonable without pretending of being the best one. It just work. I don't want to spend much time on this. It's very much consistent to what they do in Los Angeles. The maximum total shift length is 12 hours. Most of the shifts run approximately from 6 a.m. to 6 p.m. The vehicles begin and end their shift at the depot of their corresponding regions. For each depot, the algorithm fills up a vehicle at a time, starting with the one with the bigger capacity currently available. All the customer requests are inserted in the current schedule, if feasible, to minimize the additional distance to be traveled. Again, there is a lot of talk about that. I just don't want to spend time on it. And then additional vehicles are filled up until all the requests have been scheduled. In this case, you get a solution of the scheduling solution, which is feasible, but it's clearly not an optimal solution, but we used it. And here are finally the result. The result for the zoning. You can see what happened. Let's explain what is this. You have the northwest, east, south all together is basically the no zoning solution, which is not in place right now, but we simulated. And the solution, the situation which is currently operating in Los Angeles is the first one, northwest, east, and south, separated, 4 different independent zones. Number of vehicle used with this simulation analysis and the available data is more or less 500. Total miles driven is 113. Dead-end miles, 34,000. Passenger miles, 193,000. And then idle time, 45, more or less 45,000 minutes. And as you can see, here is the, let's call it half zoning, when you put together north and west and east and south. And here is the other solution, north and east together and west and south together. And as I said before, this is the no zoning altogether. As you can see, if you remove the constraint of the zoning, the number of vehicle decrease, because again, you remove the constraint so you can use your resource more efficiently. And you can see this trend also in the other performance measure, like the total miles are reducing, the dead-end miles as well. The passenger miles are not significantly increased, so it really doesn't change much for the passenger. And the idle time also is decreasing proportionally. Questions? No? Good?
So is this
Yes.
per day? This is the result?
Yes, this is per day, yes.
I was wondering if there are any intangible component advantages to having zones such as the operators might be more familiar with the street network or something like that.
Yeah, and I got that at the end of the talk. I want to mention that, of course. Otherwise, they wouldn't do it, right? So there is clearly an advantage of a managerial advantage, geographical advantage, or as you said, driver familiarity advantage as well, which is not included here. Here I just want to quantify what is your cost once you do that. Okay? So I have this advantage, but what is the cost? Right. Any other concern, question? No? So to summarize what we just saw, the effect of the zoning, for zone, as opposed to the no zoning, we have these effects: increase the needed resources of the vehicle by about 15%, total miles driven increased by about 10%, the dead-end miles increased by 40%, and the total passenger miles remains the same, and the total idle time increased by 15%. And as you just said, here is other effect. The list is probably longer. I just didn't put it here. It needs to be balanced with the above cost. And then this is in addition. Basically, the study on the zoning is finished, but in parallel, I did also, since I had the simulation already ready, I just changed the parameters for the time windows and see what happened if we increase or decrease the time window for the pickup. What is going to happen again? What is the effect in our performance measure? As you can see, the base case that I should have probably put it in bold, but here it is. This is the same case we saw before for the zoning, which is what is actually used. Let's see what happened if the transit agency decided to increase or decrease the time window for the customer. As you can see, the smaller the time window, the higher the cost for you to serve the customer, because you increase the performance for the customer, so you're going to have to spend more with your resources. And instead, you can see here, if I increase it, the number of vehicles and every other parameters is going down. And to see this in a better way, I also put it in a regression-like chart. Again, as a function of the time window, this is the number of vehicles, and is more or less, probably is not linear, but is close enough to linear. Seems much more like a curve, doing like that, but I just approximated like a linear regression, and I found the formula. And I did the same for the total miles and the dead-end miles and the passenger miles as well, and the idle time. I just keep very quickly over those. Basically, I'm saying the same thing with different parameters, but I want to show you the summary, which is basically for each minute added to the time window, we found this effect, that each minute is going to cost to the Los Angeles Transit Agency about two less vehicles to be employed. Of course, if you add minute to the time window, it's in favor of the transit agency. 260 miles less to be driven, only for 1 minute added. 200 dead miles less to be driven. 530 increase in the passenger mile, and 750 idle minutes less to be waited. So this does to give the transit agency an idea of what each minute added or taken away is going to cost to them. Conclusion and future research. We did a simulation study over LA County. We real demand data, the quantification of zoning strategy effect on performance, and the quantification of the time window of the effect on the performance of the system. It's a rough benchmark for other area, and as I said at the beginning, I'm currently working on a Houston case where they do not have zoning. But again, I'm not done yet. And the question that what is the effect of employing different scheduling algorithm may be tailored to the particular zoning strategy that you decide to employ. And especially, I didn't do it, but what is the effect of the other alternative zoning strategy, which is the one with the transfer? How much more or less you have to increase your cost if you want to employ the zoning with the transfer. And basically that's it. That's my talk. See if I know the slide, if I forgot about it. No. If you have any additional question, I'm happy to try to answer. Yes.
Thank you. I have a couple of questions. Do you know how many paratransit agencies in the U.S. really use a route optimization software or system for their route choice?
Oh, well, I believe all of them used it.
Oh.
Unless they are very, very small agency, local agency, but I believe they could not do without it if you have too much demand.
So what is there any most common algorithm they use or no?
First of all, these are proprietary software, so we don't really know what's behind it. Even we might guess, but it's not something that it's to the public. Right? They use heuristic. They cannot get optimal for sure. The problem is too big to solve. But I'm not sure exactly what they use to solve it. Yeah.
And my second question is, I wish you could explain a little more about the algorithm that you use in your simulation.
Oh, the one that skip a little faster there? Well, let me see if I can try to make you understand. First of all, I have to remember it. No, it's based on a simple insertion algorithm. I don't know if you're familiar with insertion algorithm. Insertion algorithm means that you take one customer at a time and you insert it in the current schedule that you are trying to build. And you put it between the two already existing customers, and you choose the one that is going to minimize your additional distance. Is it clear enough?
Yeah.
Okay. And you do that until this particular bus or vehicle that you are trying to fill up cannot take any more customers. Okay? So every time that you try to insert a new customer, you need to check the time window are fine, or you need to stick to the rules. Okay? You cannot, violate the time window. You cannot violate the maximum travel time for each one of the customers. And each customer needs to have 2 points inserted, pick up and drop off. It's not only one, so it's getting a little bit more complicated. But this is the base. So what we use is using this for, you start with one vehicle, actually the bigger vehicle available, and you fill it up in this way until you cannot take any more customers. You try all, and you fill it up. And then you put it aside. And then you check the capacity of this particular vehicle once you are done, and you see if any smaller vehicle can actually do the job that you are just done. If it's possible, you switch it. So to try to optimize again, so you have a larger vehicle still to be used. Okay? And you do that, you do this procedure until all the customers are served, and until, of course, hopefully you don't finish your fleet. Most of the time you have still available fleet. But this is the scheduling algorithm. That is definitely not optimal. It's probably not what they use, but it's close enough. It's one heuristic available. And again, I didn't spend much time on it simply because it was not the scope of this particular study. I just make sure that I use the same one in each one of the cases we did. Yes?
Do you have any numbers on how often the drivers were on time in a designated time window?
That's a good question. No, I don't have a number. And I'm sure that due to traffic condition or any other random event, that's not always the case. But no, actually, I do not have a number of that.
I was also curious to see if you can offer up how the different providers manage being on time or set goals, et cetera.
Say it again, what kind of question is it?
There are different providers in Los Angeles County, right?
Yes, each zone has a different provider, yeah.
They all have metrics that they go by?
They all have to follow the same 20 minutes maximum time window and 2.5 maximum total travel time. They always have to do that. I don't know if they use different algorithms. I don't know if they use all the same. I don't have this data, so I'm sorry, I cannot answer. Yeah. Yes?
I just had a question about the time windows. Is that always like a constant maximum that they have to do, or is it a variable?
As I said, different cities use different time window setting. In Houston, they actually have 40 minutes. And if you call, let's say 9 o'clock, they're going to say, okay, we'll be there between 20 to 9, 20 past 9. That's your time window. Los Angeles, they're much stricter. 20 minutes is half of it instead of 40. So.
Okay, but they never vary it like within the network. It's always.
No, as far as I know, no. It's the same. It's the same for all vehicle, all customers. Yeah. Yes.
That 20 minutes, is that based on survey of ridership? Is that the max they're willing to wait? Or is that number come from?
Oh, that's a good question. I'm not sure. I'm not even sure what exactly is the mandate from the federal, because since the cities have the option to use different values, I don't know where it comes from. Maybe they have a maximum that they cannot go over, and then they can choose to make it smaller. But I don't know if they come from survey, or I don't know exactly where they come from. Yeah. You need to have this value in order to have a flexibility of your scheduling, otherwise it would be too hard to fulfill. Yeah. Yes?
You mentioned earlier majority of the work, I think scheduling is done manually.
No, I said the majority is done, I mean, most of the work is done by the software, but at the end the solution is manipulated by the actual operator manually, because they don't like something, the driver has some kind of request that was not in the scheduling algorithm, and so they adjusted in the morning.
My other question was, is the software being taught in schools to get people ready to use it and be more effective, heavy using the software?
I don't think that they teach it in school, but maybe they have the actual software provider. Of course, they're going to have some training session for the transit agency in order to use it. Yes, it's not. I saw it, and it's like a window-based software, but you need to learn it how to use it.
Thank you. I've got a question in particular about the relationship with the service agency. So, was your research connected to the actual agency that was organizing this, and what kind of recommendations did you make, whether it was in that time window, to try and create more efficiencies or whatnot? I find in academia that we do work quite often, but we don't link it to practice, so it seems like this would be applicable.
Well, this was very applicable. Actually, I was working myself with, I forgot the name of the agency right now, but we were working closely back and forth. They give us all the data that you saw here. And as far as the recommendation, we give them the report, and they do what they need to do with, they have, I think, the pretty good information for them to see what will be the effect. Maybe not about the zoning, because it's probably more difficult to, like tomorrow we don't do the zoning anymore, but they might change the time window to see, okay, if we add 5 minutes, we can avoid using so many more fleet. I don't know if they did it or not, but that's the feedback we gave it.
In your opinion, would a 5-minute increase in the window then be optimal, or would it be something more along the lines of 30 minutes rather than 20?
Oh, I don't know. It's hard to define the optimal here. You have two different objectives: the customer satisfaction and your own cost. It's always very hard to find a balance. So this is also why you don't have a unique way of doing stuff. It's like it's a Pareto optimality solution. I don't know if you're familiar. You have different points where you could choose from, and you need to make the trade-off yourself. It's hard to optimize only one point. You can see what the delta is between one or the other. This is what's important for the decision makers. Yeah. Yes. I thought you had a question.
Yeah, I worked for an agency that managed some of these programs, and it was a big source of revenue for the agency, and there was a lot of sort of competition within the varying providers in the city, and so it might be difficult to move away from the zoning system if you have
of course
interest, right?
Yeah.
So I'm wondering if there would be ways to maybe improve the zones themselves to more accurately reflect trip patterns. For example, if you know that a lot of people are going from this one zone to a certain hospital, for example, could you change the boundaries of the zone and therefore improve efficiency?
Absolutely, I agree. If you want to keep the zoning, make it demand dependent would be the best way to do it. But as you can imagine, it's not some easy task. But I agree that you could find some improvement if you do some kind of study like that. Yeah. And it could be done by simulation as well. Maybe you need to do a lot of other case to study, but sure, I agree. Yeah.
I noticed from the trip distance histogram that it looked like the average trip distance that you used were a little higher than the actual ones, which I assume would make a worse case for zoning than lower average trip speeds. Did you look at all at how, say, the mean?
Oh, let me see.
How the mean trip distance would affect the result?
Yes, for sure it would affect the result. You know, the simulation is not a perfect replica of what's actually happening there. And I agree that the actual distance, average distance is higher than it would actually happen. I'm not sure if it's good or bad for the zoning itself. I should look a little bit into it. But I'm sure that there is some effect that we didn't consider. The reason why the actual distance are a little lower than the simulated one is because, at least this is what we think, is that if somebody wants to go to a hospital, generally goes to the closer one, and not to any other random one. So instead, we made the assumption to independently sample pick up and drop off. So in this case, you make the distance a little larger. But as you saw in the histogram, the distance, the two charts were not very different. So we assumed it was a good assumption. Very hard to make it exactly as it is there.
Sure. Okay. Quick follow-up to that. For the trip distances, are the, I don't know how the fee structure works for the riders. Is it distance-based at all, or is there only cost travel time?
Actually, I'm not sure how the fee structure is there. I know that they are highly subsidized by the federal government, and I'm pretty sure maybe I shouldn't say anything, but my guess is that they have a constant fee for per trip. But they might also have some discount if you do regular use of the service. Actually, but again, I don't want to say much about it because I'm not very sure what's going on there. Yeah. Yes?
Does the paratransit service in LA use GPS? And do they actually have more detailed data available? Or do they only have trip starts and ends? Do they actually have route patterns?
The data that they give us, it's only a very detailed log for each customer at where it is, when it was picked up, what was the time window, what is the distance, what is the we have all the data needed for the actual pick up and drop off data. But I didn't see any GPS. At least they didn't give us anything related to GPS. But my guess is that they might use it, but I didn't see it. Yeah. Any other? Yeah.
You might have mentioned this, but with the time window constraints, does, I guess in practice and with the program, does it allow multiple vehicles to potentially meet the time window constraint if there's travel time variability? Like if one is en route to pick up a customer, but they can't meet the constraint because of traffic delay, got another vehicle.
I'm not sure if I understand the question. All the scheduling is done before. It's not done in real time. Actually, some of it is done in real time, only if you see feasibility. Some customer ask for emergency transport, and in that case they do some adjusting. But I don't think they account for which vehicle would do a good job because they do everything beforehand. I don't know if I answer or I understand your question correctly. I'm not sure. Yeah. So I'm thinking about the scheduling is done many hours before the actual condition, right? So, but I'm sure they do adjusting during the day if an unexpected event happen. So in that case, they try to fix it. Yeah.
So as the population is getting older and I guess more people start using this kind of system. And I guess also congestion is also kind of doesn't get better over time. So what are the new solutions or the new ideas that agencies have with technology maybe, or what are the things that are being done to innovate in things to deal with the problem?
Well, it's a good thing. I think the only thing that comes to my mind, it's a good estimate of the actual travel times. This is what, in order to take care of the future higher congestion, would be higher travel times. So when you do the scheduling beforehand, instead of taking 20 minutes to get from one point to the other, it takes more. So you need to change that. And in this case, I would say real-time data, but as I said, in this case, it's all done beforehand, so you don't really use real-time data. But you might want to use the data one day for the next day and so forth. So this kind of update. And I'm quite sure they do that. If they don't, they should.
So in Europe, is it the same operation, or is it different from the
I'm not sure. I never heard about this such a huge business for paratransit like here, honestly. And I don't know how they do it here.
I can talk a little bit to that.
Sure.
I know that it's very common in certain Scandinavian countries to use taxis specifically for their paratransit, and it's used in other countries as well as a way of kind of economizing trips, because those fleets exist already and they're already private pay. So I don't know about other countries. So.
Yes.
I have something to offer to that as a follow-up. In the United States, in the city of Indianapolis, they also use the taxis indirectly for paratransit. For one thing, the regular paratransit could not meet the demand, but they give a discount coupon books. They would allow certain people with disability to buy coupon book
and use a taxi.
With a heavy discount.
Right. Actually, I think they do something similar in Houston as well. The study that we are doing right now. I don't know if they do this discount technique, but they have a fleet which include also some taxi drivers. Yes.
My question is it's kind of two-part, but you're talking about no-show time.
No-show.
No-show. You're trying to minimize that. I guess what ideas do you have towards minimizing that part of it, and then also with the pickup trips, do you find is there any issues with customers, sharing vehicles going into two different points?
Well, I'm not sure I'm sure that people would like to have their own private vehicle, to answer to your second question. But some of them have, maybe with a taxi, but generally it's a shared ride. Right? About the no-show, what can you do? First of all, I should have mentioned that at least in Los Angeles, when I was there, if you get a pickup point, and the rule is that if the customer doesn't show up for 5 minutes from the beginning of your show-up time, then you are allowed to leave. Well, sometimes they call and they wait more, but generally it's 5 minutes. How do you minimize that? They have, if a customer should no show for 3 times in a month, if I remember, then it's no more considered for service in the future, or at least he needs to wait for a couple more months. So you try to minimize that by, telling the customer they need to be good. If they call, they need to be there, but they still have a high percentage. 10%. Well, I don't know if it's high or low, but it's significant to me, of no show. And other than that, I don't know. That's a good question. To minimize that, it might be. You might have an idea or someone. Any other?
I think we'll thank our speaker, but before that, just remind you that next week, Salita Reynolds from Fair and Peers will be presenting multimodal level of service, state of the practice. And so let's thank Professor Quadrifoglio.
Thank you.
I'm Hadi, PhD Purdue.
I think I saw you already somewhere, in some TRP maybe or something.
What is the Maybe a too simplistic question, I forgot my simulation. But why don't you use the actual network for Houston, for Los Angeles?
Because it's very hard to implement, to calculate the distance in the actual network. This is what you need.
You don't have that?
We didn't have it at the
You
time.
don't have the matrix?
No. We only had the location, and we assumed that the distance was like linear. Of course,
I
it's an
think the
assumption.
network exists in
does.
digital form. Someplace. I know that.
With all the distance between any pair of points.
Right.
If it exists, we should have used
the
it.
transportation agencies have it.
Okay.
You know, in Houston, for example, it exists.
Okay.
Just a recommendation. The average distance is good for simulation. The average speed is good for simulation, but it doesn't. It's not helpful to the client